communities of quantum information and high energy string theory, which is one of the aims of the workshop. So please, Alex.
So yeah, thanks for the organizers for putting this workshop together and for inviting me to give a talk. And my goal here is to give an overview of quantum complexity theory, but a bit different from what we see normally in theory complexity, and see other notions of complexity, for instance, about quantum proofs. But before I start, I'd like to give some disclaimers. So first of all, in complexity theory, we usually cannot prove unconditional results. So usually we build this house of cards where we have some assumptions that we strongly believe, and then from that we derive some conclusions. And I'll try to make it clear when we can prove things and when we believe things to be true. But you should have in mind that usually this is the case that we just have some strong intuition that a result should be true instead of proving it. And in our defense, we have these unconditional results because we cannot say, this is how nature should behave and just accept that. So of course, it's a joke, but the point is, yeah, we don't know how to prove things formally. The second disclaimer is that, as you probably have seen in this slide, so first, we love acronyms, and I'll try to avoid them. I won't succeed, so please interrupt me and ask me if something's not clear, and I'll try to remind you the definitions of these complexity classes and that you see. And finally, I'd like just to tell you that I won't mention black holes, ADS, CFT, holography, or anything like that. And I think the goal is trying to explain a bit what we have been doing in quantum complexity theory and see if there are something in common and that can be bootstrapped some kind of new area in the intersection of these two fields. So having said that, let me start. So first, let me tell, what do we want to do with complexity theory? And the main goal is trying to understand how hard or how easy a problem is. And here, a problem, it can be defined as like a problem can be very, very, very different from each other. So for instance, you can just have, I don't know, you have a graph and you want to find what's the minimum, the shortest path between two nodes, or you're given a description of Hamiltonian de-Ising model when you want to compute the ground energy, and so on. And you want to solve this problem, right? But one thing that we want to measure is, as I said, the hardness of this problem, but we're interested to do that in the asymptotics. So we want to know how hard this problem is when you consider that the input to this problem tends to infinity. And the idea here is that, for instance, that we don't care too much about concrete examples. So for instance, if you want to compute the ground energy of Hamiltonian of a 2 to the 100 particles, we find that's easy because it only takes constant time. So, but now when we consider that, you have a family of Hamiltonians and the size of the number of particles tends to infinity, then we can have a more concrete measurement of how hard the problem is. And this is our goal, and how do we do it? So first, we have to define a computational model. So for instance, we can consider deterministic or quantum computation. We can also consider that this computation has some help of an advice or proof. So first of all, we define what are the rules of the game. Secondly, we try to define a set of a complexity class. It defines it put some bound on the resources that we want to be allowed in this computational model, and we try to understand which problems can be solved in this complexity class, or which problems are not in this complexity class. A very important line of work is trying to understand which problem encompasses the hardness of this class, meaning like what problem somehow is the example of this class. So if you solve this problem, you solve this whole class or complexity class. And finally, you want to understand how complexity classes they related to each other. Okay, and I'll show in this talk a lot of examples of these type of questions for quantum complexity and quantum proof systems. And the goal of this talk, I'll quickly talk about which problems are easy for quantum computers. Then I'll move on to which problems we expect to be hard for quantum computers. And then I'll focus on the connection of these hard problems with physics. And just to be a bit more precise, in this talk, I consider only decision problems. And the idea here is that I consider problems whose answer is yes or no. And this is formalized from a complexity theory perspective, is that you have two sets of strings. So you have two families of strings, yes and no instances, and they are disjoint. And the problem is you're given one input that's either a yes instance or a no instance, and you have to decide which is the case. And some examples, for instance, is, okay, given a number n, does it have a factor in the interval from L to L plus K? So this is the factoring problem, but it's decision version. Or also, given a Hamiltonian H, the description of Hamiltonian H, then is its ground energy smaller than alpha or bigger than beta? And here usually we don't consider that alpha equals to beta, but we need some gap between these values, and this is called a promise problem. So you promise that your Hamiltonian has either ground energy smaller than alpha or always larger than beta. And I'll tell later like why these kind of promise problems are important. So let's move to problems that are easy for quantum computers. And as I said, the first thing that you have to do in complexity theory is defining the computational model. And for quantum computation, we have several models that are shown to be equivalent. But for this talk, I'll focus on quantum circuits. And in quantum circuits, so we know that from quantum mechanics, the evolution of the quantum systems are described by unitary matrices. But here, when you want to talk about complexity, you need to be a bit more fine-grained. So which type of unitaries are you allowed to use? And for that, you need to first fix a universal gate set. So for instance, let's say that you're only allowed to do 1 and 2 qubit Cliffords and T gates, or Hadamard's and Toffoli. So you have to define what are allowed tools in order to construct a quantum circuit. Once you fix a gate set, then we consider that a quantum circuit is just like composing these quantum gates. And the idea is that you're given as input to this quantum circuit, the input to your problem. So you know if, for instance, a string X is a yes instance or no instance, but we're also given some auxiliary qubits initializing 0 that you want that you need for some workspace. And then you compose, as I said, these gates from a fixed gate set. And finally, for decision problems, you measure we consider that you measure the first qubit in the computational basis. And then you decide to accept or reject based if the output is 0 or 1. Okay, so this is the computational model that I'll be considering in this talk. And having fixed that, then we can talk about what are the complexity class of problems that can be efficiently solved by quantum computers. And then we can define what we call this complexity class called BQP. It stands for bounded error quantum polynomial time. And the idea is that you want a promise problem. So you have yes and no instances. And you want to say that there is a family of circuits that scales like one circuit in the family for each input size. And the idea is that this input, this circuit here receives as input the input to your problem. So the instance that you want to know if it's a yes or no instances, and then the ancilla qubits, and then, as I said, it applies some gates and then decides to accept or reject based on the measurement. And then you say that it's in BQP. First, the number of gates in this circuit scales polynomially on the size of the input. And then for yes instances, you want that the output of this qubit is 1 with probability larger than 2/3. And the probability that the output 0 for no instances is also larger than 2/3. Or the probability that the output 1 is smaller than 1/3. Okay? And in complexity theory, so if you want to then to say that a problem is solvable by quantum computers, then we just have to show that this problem is in BQP. We have to show such a family of quantum circuits with these properties. And we know that there are a lot of problems in BQP, not as much as we wanted, but we know how to solve factoring, or we know how to solve linear system of equations much more efficiently. And also, okay, you can also think about other types of complexity classes that could define an efficient quantum computation. So, for instance, you would like a quantum circuit with constant depth, or like these near-term quantum proposals for random circuit sampling or boson sampling. But from a complexity theory perspective, we usually are only interested about polynomials. So I will stick to BQP and its variants through this talk. And okay, this is my, so is it clear? So can I move on? So please ask me questions during the talk.
I'm just wondering. Sorry, I'm just wondering whether it's uniform sequence of circuits or.
Yeah, it's uniform. So yeah, I didn't want to put too many buzzwords, but for those who understand what it is, it's a uniform family of circuits.
Why are you not requiring that if X has a no answer, the probability of outcome 1 is bigger than something?
Sorry, if it's if it's no, okay, I want that that you output 0 with high probability. So a different way of saying is that the probability that you output 1 is small.
That's equivalent. Okay.
That's equivalent, yeah, because it's a qubit. So if you measure in the computational basis, the output is either 0 or 1. You have no other choice.
Okay, yeah, sorry.
And do you have any constraints on the memory or space, or how much?
So yeah, the circuit, as I said, the circuit it scales polynomially of the size of the input. So the space has also to be polynomial. But we're not fine-grained. It's just about being polynomial in the number of bits of this input X. Does this answer your question?
Yes, thank you.
Okay. Okay, so but this is a talk about complexity. So I want to focus on easy problems, because in complexity we like to show hardness usually. That's the key thing, like showing lower bounds. And the question is, so which problems are hard even for quantum computers? And for that, we use a very important complexity class from classical complexity theory. And this problem is called, this complexity class is called NP, maybe you've heard it. And this class tries to define what you mean by efficient, not efficient computation, but efficient verification. So the idea here is that you want you want to have a classical algorithm, and again, you receive an instance that you want to decide if it's a yes or no instance. But on top of that, you receive some untrusted proof from some third party that you call the prover. So the prover provides you a proof to your statement, but you don't trust this proof, so you want to verify if the proof is correct. So the idea here is that, this algorithm D, given a mathematical statement and its proof, check if the proof is correct. Okay, and we say that a problem is in NP if for all statements that are correct, there is a proof that makes this polynomial time verification algorithm to accept. And for no instances, so for wrong statements, no matter which proof is given to you, this verification algorithm will always reject. And here, for instance, so as an example, so if you have an Ising model, I can give you the description, like I can give you the ground state. I can tell you what the ground state is, and you can, using this, you can check if the ground energy is smaller than some value alpha or bigger than some value beta, right? Because you can just compute the ground energy yourself if you have a candidate for the ground state. And this complexity class NP is a cornerstone of complexity theory. So it has far-reaching applications. So it's used, like, it's very important even in practice. And it's strongly believed that NP is not contained in BQP. So it's strongly believed that we cannot solve this important class of problems even with quantum computers. But on the other hand, we also strongly believe that BQP is not in NP. So, so in some sense, these two types of notions, like having a classical proof and having quantum computation, is somehow two incomparable type of resources. So the question then is, so okay, we have this definition for classical verification. So one of the questions is, so can we go one step further and define what a quantum verification algorithm should be? And this was the notion that was defined by Kitaev in '99, where when he defined the complexity class QMA, and this stands for quantum Merlin-Arthur. And now, instead of only giving a classical proof, you have a prover that's allowed you to give a quantum proof of some statement. And then you have a quantum algorithm that, given this classical input and this quantum proof, decides to accept or reject. And now we want that if it's a yes instance, there is a quantum proof that makes this quantum algorithm accept with high probability. But for no instances, no matter which quantum proof this prover gives, the probability that this quantum algorithm rejects is large. The probability that it rejects is higher than 2/3. Okay, and from a complexity theory, you see that, okay, this is a very straightforward definition. So it's a straightforward generalization of NP. So from a complexity theory, it makes sense. But okay, is it connected to other things? So does it have the same influence as NP? And this was like in the result by Kitaev, where he defined QMA. He actually showed that this class has a very important complete problem. And this problem is very, very important in physics, and this is the local Hamiltonian problem.
Can you say what is the acronym of QMA?
It's quantum Merlin-Arthur.
Why?
Oh, because, okay, you have NP, and here you have a deterministic algorithm. Then you could consider the intermediate step where this verification algorithm is randomized. And when it's randomized, this is called Merlin-Arthur gains, because then you assume that the prover, like the Merlin, gives Arthur this proof, and then you're just extending this Merlin-Arthur to quantum, like, because strictly speaking, like, this is a more generalization of probabilistic verification than deterministic one. So that's why you use quantum Merlin-Arthur. So as I said, okay, so Kitaev also considered the following problem, the local Hamiltonian problem, where the input to this problem is a description of Hamiltonians H1 up to Hn, each one acting on k qubits out of an n qubit system. And now you should see, like, n tends to infinity, so n is the parameter that you're increasing, but k is a constant, let's say 2 or 5. Okay, so you have these Hamiltonians on acting at most k qubits. And then we want to understand the ground energy of the global Hamiltonian. So the Hamiltonian that consists of the sum over these local terms. Also, okay, just a remark. So also you assume, for instance, that these local terms, they have norm at most 1. So you have to somehow bound this norm, but let's assume without loss of generality that this bound is 1. And then your question is this following. So is the ground energy of H smaller than alpha m? Or the ground energy is at least beta m for some beta. And what Kitaev was trying to understand is when this problem how hard or how easy is this problem based on these betas and alpha. And what Kitaev showed in 99 is that actually this problem is QMA complete when beta minus alpha is an inverse polynomial in N. And what do I mean by complete? It means two things. So first is that you can solve this problem in QMA. And second, that this problem somehow it represents all the hardness of this complexity class QMA. So so this problem it encompasses the hardness of quantum proofs. Let me quickly talk about these two steps in order to show QMA completeness. So the first question is, how can you solve this problem in QMA? And this is actually not very hard because we assume that you have a quantum proof. So you have this untrusted Merlin. He could give you a candidate ground state for a Hamiltonian. So he gives you a quantum state that's supposed to be the ground state of a Hamiltonian. And then Kitaev showed that you can, estimate, you have a computational process that can estimate the energy over this local Hamiltonian according to this state. So the idea is that then, given this untrusted proof, the prover can decide if the energy is low or high, if there is enough gap between these two parameters. What is the hard part is showing QMA hardness, and by hardness I mean that so for showing hardness usually you have to do a reduction. So we assume that for doing a reduction you assume that you have a QMA verification. So you assume that you start with this verification algorithm that is composed of a bunch of elementary gates. And then you have yes instances and no instances, and we know that for yes instances there is a proof that makes this verification algorithm accept. But for no instances, no matter what this prover sends, the verification algorithm should reject with high probability. And in order to show hardness, we want to show that you can map this verification algorithm and this input to this problem to a Hamiltonian HVX. And you want that the ground energy of this Hamiltonian to be tightly correlated with the acceptance probability of this verification algorithm. So in particular, you want that this ground energy, the ground energy of this Hamiltonian is low, if and only if the acceptance probability of this verification circuit is high. Okay, and this is saying that from any problem in QMA, I can give you a local Hamiltonian, and solving this local Hamiltonian, computing the ground energy of this local Hamiltonian will tell you if this input to the QMA problem is a yes or no instance. So solving this so being able to compute ground energies is the same thing as quantum verification. And so is this clear what I'm trying to say?
But if you show that it's in QMA, does it mean that you show that it's not easy? I mean, can it be still in, I don't know, BQP or something like that? So, I mean, you need to show that it's not in BQP. You have to show that it's equivalent to another problem that is QMA hard, that is like the benchmark problem of QML hard things or something like that?
So the point is, as one of my disclaimers, that you cannot prove things. So we strongly believe that BQP is not equal to QMA, so you cannot solve QMA problems in BQP, but we don't know how to prove it. And that so having this assumption that these two are not the same, then showing this hardness is then showing that this problem is probably not in BQP. Okay.
What is the benchmark problem in QMA that you translate all the problems to make it?
Oh,
like,
this is this local Hamiltonian problem. So I give you
okay.
so yeah, this is the benchmark problem.
Okay.
Okay.
Thanks.
So the first thing is showing that it is in QMA. So okay, it's not harder than this class, but so the first says that every problem in QMA. So putting in QMA says that every problem in QMA somehow is harder than local Hamiltonian problem. Is at least as hard as local Hamiltonian problem. And here we so the inverse, that also the local Hamiltonian problem is at least as hard as any problem in QMA.
And I mean, just to be sure, I mean, you could also take an easy problem and reduce it to local Hamiltonian, right? I mean, that's okay,
yeah.
right?
Yeah.
But you can also take the hardest one you can come up with, and your point is you can map it to local Hamiltonian.
Yeah. Usually when you want to do reductions, you want to reduce a hard problem to an easy one, because then you can solve the hard problem as well. And then
before you had some conditions on the gap for the Hamiltonian also. It's not.
Yeah. So what I show is that okay, yeah, if you have some gap here in the acceptance probability, then you also have a gap here. Okay, so let me, okay, I'll continue, and then if at the end of the next step slide this is not clear, let me know. Because so this QMA hardness, it was shown by Kitaev using like one of the key ideas in quantum computing is like this idea of Feynman of using Hamiltonian time-independent Hamiltonians to simulate quantum computation. And I won't describe it in details, but the idea of this construction is that given a quantum circuit, you can construct this Hamiltonian whose low energy states, they must have this form, and that you call the history state. And this is the superposition over the timestamps of your quantum circuit. So here you have the superposition of every t, so every time step of your computation, and the state of your computation at that state, at that step, right? So you have a superposition over this entangled state or t, and snapshot of the computation at time t. And what this Feynman type construction is able to do is creating from this verification algorithm, or from this quantum algorithm, it allows us to create no local terms that enforce the low energy states to have this form. And these local terms, they have different types. So so here we consider a clock. So you have to ensure that the clock is well formed. And there are a lot of things that are adding penalties when the state has not this form, but I won't get into details. But the conclusion that Kitaev had is that when you consider the Hamiltonian, that's the sum over these local terms, then he can show that if the verification algorithm accepts with high probability, then the ground energy is small. And when the acceptance probability of the verification algorithm is small, then the ground energy is high. So for a suitable value of epsilon, then you have the desired inverse polynomial gap between yes and all instances. Okay, and then these constructions allow us to somehow use the local Hamiltonian problem to describe every problem in QMA. Okay, so okay, let me continue. So as I said, so we can show that, okay, what Kitaev showed is that there is one parameterization of the local Hamiltonian problem that is QMA hard. And the question is, how far can you push this hardness result? So, so instead of having a general local Hamiltonian problem, can you put some constraints on it and show that this problem continues to be hard in this case? And in particular, we would like that, these Hamiltonians that come from the reduction of Kitaev, they're very they're not realistic in some sense. Like there are Hamiltonians that they're not the type of Hamiltonians that one would expect to encounter in nature. So in particular, one important question is: can you have more physically motivated Hamiltonians that are that computing the ground energy of these Hamiltonians is QMA hard? Another very important question that I'll try to address is that can you also show hardness when this gap between beta and alpha is not only an inverse polynomial, but also a constant? And notice that when the gap between beta minus alpha is larger, this problem becomes easier, right? Because like it continues to be in QMA. And the question is this problem still hard? And so let me talk a bit about this point. So one of the first questions is, can you, for instance, show QMA hardness for geometrically local Hamiltonians? And for instance, can you show that if a Hamiltonian is now only nearest neighbor interaction on a 2D lattice, is this problem QMA hard? And this actually was shown to be true even for qubits in a series of work. I think the last one is by Oliveira and Terhal. And then the question, of course, is, okay, you have a 2D lattice. Can you have a 1D lattice? And yes, we can. So we can show that for the local Hamiltonian problem in a 1D lattice is also QMA complete, but now not for qubits, but for the local dimension of each side has to be at least 8. And finally, we can also ask more questions. So can you have hardness of translation invariant local Hamiltonians? So for translation, also the difference here is that in 1D lattice, we will allow these terms, the terms over different pairs of qubits to be different. And now we want to have just one local term. And this local term will be repeated on every nearest neighbor over this 1D lattice. And at the beginning, so what was showed first by Gottesman and Irani, and then by Bausch, Qubit, and Ozols, is that this problem is not QMA complete, but it's QMA X complete. But and also the local dimension is high. But this exponential is saying that, okay, you need a proof that's exponential, but exponential in the size of the input. And it's not, so yeah, it's a tricky thing is that it's not that the problem became harder, it's the instance became smaller. Because when you're talking about translation invariance Hamiltonians, the input is the following: a local term and the number of qubits of your system, right? You don't have to say anything else to describe your problem. And now to tell you that the ground energy is small or high, I have to give the ground state of n qubits, but the description is just log n qubits. So that there is this asymmetry between how many qubits you have to send and how many bits you need to describe the size of their input. Okay, but just to tell that, okay, this QMAX, okay, at least the first time I saw it, okay, I got surprised, but then you understand that, okay, it's morally the same thing, but just a different scale. And there are even other QMA families that are also QMA complete, both Hubbard models, antiferromagnetic XY, and so on, and a very nice characterization of families that are QMA complete can be found in this result by Qubit and Montanaro. And it really tells you when your Hamiltonian is QMA hard, or it has other complexities. And one curiosity, and I have never seen it I have never seen this connection being formally proven, but it usually happens like that, is that you can prove QMA hardness of computing the ground state of Hamiltonian when you show that this Hamiltonian is universal for quantum computation. So I think it's a very interesting question if this connection can be actually be formalized, and you can prove that, okay, instead of proving the two things, just one is sufficient. Any question? So let me continue. So I started considering some restricted families of Hamiltonians, and then we can restrict even more. So for instance, what's the complexity of Hamiltonians without the sign problem? And from a quantum computer science perspective, these are called these stochastic Hamiltonians, and they model somewhat these first D-wave computers. And the idea here is, so you have the original local Hamiltonian problem, but we assume that each of these local terms does not have the sign problem. So formally it's defined that like in the standard basis, the off-diagonal elements, they are non-positive. So this is the formal definition. But the idea is that, okay, you can have a more operational way of describing them by saying that they don't have a sign problem. And in this very beautiful result by Brave and Terhal, they show that actually the hardness of this problem when alpha is equal to 0. So you want to know if the ground energy is exactly 0, or at least an inverse polynomial. This is MA complete, where MA is again the randomized version of NP. So this is very surprising, because before this result, we didn't know any complete problem for this class. And this result shows the first complete problem, and it comes from quantum computing. So I think it shows that, okay, studying quantum complexity is not only like it is beyond quantum somehow. Like we can also solve problems in classical complexity theory by studying quantum. And then this result was for different parameters, it was proven different hardness. So we have here like a variety of hardness of these problems. And in particular, it is a very important and long-standing problem in classical complexity theory, is that randomized verification is equal to deterministic verification. And we have evidence to believe that these two are the same. And in some sense, with this result of Aharonov and me, we showed that, okay, actually this problem of de-randomizing verification algorithm is tightly connected with the complexity of computing ground states of some type of Hamiltonians. So now switching gears a bit from Hamiltonians, going back to verification. To different ways of showing hardness of problems in a different axis. So as I said, Kitaev showed that the local Hamiltonian problem is complete for QMA. So even it's hard for QMA when you have an inverse polynomial beta minus alpha. And the quantum principle conjecture asks how hard is this problem when you have a constant beta minus alpha and some constant k. And this conjecture, so for me, is one of the most exciting open problems in quantum complexity theory, and it has also tight connections with some physical problems. So for instance, it's highly, so in some sense, this question is asking how entangled are excited states? Because as it was shown by Brandau and Harrow, like there are families of Hamiltonians for which all excited states are tensor products, and in this case, if these excited states aren't tensor product, they're not supposed to be QMA hard, assuming complexity theoretical assumptions. another connection between, another question around the quantum PCP conjecture now on error correcting code is, can you have locally testable quantum error correcting codes? So meaning like, can you have a quantum error correcting code such that you can test, you can have these check constraints of this of this quantum code word, and somehow you can say that if your quantum state is delta far from your code word, then function of delta constraints will be rejected. Finally, this is also connected. It's not directly connected, but morally it is, like, to area law. So area law says that the ground state of Hamiltonians, so if you put a Hamiltonian on a lattice and you consider a cut over the lattice, so the entanglement between if you consider the ground state, the entanglement between the two regions scales as the area and not as the volume of this cut. And in some sense, this area law is somewhat the opposite of quantum local Hamiltonian, like the quantum PCP conjecture, because it's saying that, okay, there is not too much entanglement between these two regions. So maybe they can be approximated by MPS or Miras or other family of states. So maybe showing that such families, like when you put on a lattice, you have area law, is somehow, it could be, it's not directly, but it could be disproving the quantum PCP conjecture for this type of Hamiltonians. And finally,
Alex,
yes,
you're running a bit late on time.
Okay.
How much longer?
So okay, I'll talk a bit about some variants of QMA very quickly. So for instance, we could consider when you have a quantum verification algorithm, but now you have a classical proof instead of a quantum one. And we believe this tool to be different, but actually we don't know how to do it. And so there are a lot of open problems like in this direction. So a different notion of QMA also is, instead of receiving only one proof, you receive two or more proofs, but you assume that these proofs are not entangled. So you have a product of two quantum proofs, and surprisingly, this complexity class seems to be much more powerful than QMA. But we don't, we have a very narrow understanding of it. So this is the power of unentanglement, actually. Finally, we can consider not, okay, now I told you some cases where the prover can send a quantum state and the verifier checks it, but you can say, why can the verifier also ask questions to the prover? And then you have a quantum, what we call quantum interactive proof system. This type of proof systems, you understand it much more because it's actually equal to classical interactive proof system. So quantum does not add, in general, quantum does not add computational power in this case. But on the other hand, if instead of having just one interaction with one prover, you have with multiple provers, in this breakthrough result of this year, this model was shown to be very powerful. So it can solve even problems that are not computable, and solving this Connes embedding conjecture from operator algebra. So sorry for running out of time. So I wanted to give you some of the fundamental results that we know from quantum proofs and trying to do some connection with physics. But there's much more that I didn't have time to talk about. And I think the important thing here is that this type of results, they have a tight connection with the problems in physics. And one of the question is, can you show hardness of, let's say, some Hamiltonian that has some inspiration on black holes or holography or so on? So my question is very vague because I don't have any candidate for that. And I think this workshop maybe could put us together and try to find what a candidate should be. And thank you for your attention.
Okay, let's thank Alex for this nice introduction.
Oh.
And we have time for more questions.
Peter?
Yes, I had a puzzle with your basic reduction you had to these Hamiltonian separations of state. The very first reduction you gave. Even before this one.
This one?
Yes. The problem is that if you see these two expressions, C epsilon over M versus C prime 1 minus square root epsilon over M cubed, it doesn't look much like a gap because 1 over M is decreasing much slower than 1 over M cubed. So how does the increase of the various parameters work here?
So sorry, yeah, there are some things that I didn't say. That, for instance, in QMA, we can, like, this error is constant, but you can make it exponentially small. So
Yes.
we can assume, you can assume that epsilon is exponentially small. So this is exponentially close to 0, and this is 1 minus square root of epsilon. So this is exponentially close to 1. So this is an inverse polynomial.
Yes.
Like if epsilon is exponentially small, this is an inverse polynomial, and this is an inverse exponential.
But how is M to be taken constant here?
M is polynomial in N. So M is a polynomial.
So
because
you
because
really have to look at all the quantities to see that it works out the right way here.
No, yeah, okay, but the point is, M is the number of gates in your quantum circuit, and
Yep.
by definition in QMA, this M is polynomial in N, like a polynomial in the description. So that's why, like, if epsilon is an inverse exponential, if epsilon is an inverse exponential and M is a polynomial, then you have the gap for any constant here.
Thanks.
Maybe I can ask something. It's more from the HEP perspective, but I was wondering if there is a value or a field of people that look at the, say, exact complexity of constructing specific unitaries. Because when we talk, say, about this like linear growth, etc., we are interested in taking a set of rules and evaluating the, say, exact complexity of a given unitary. And if that is value outside, like putting them in generic classes, etc.
No, I think it has a lot of value. Specifically, for instance, if you want to implement them, or like sometimes you want to have a fine-grained measure of complexity, and then in this case, then you have to do with this, right? You have to really count how many gates you need or which type, and then even the type of gates that you have would matter. But usually, like in complexity theory, even with this loose definition, we don't know how to prove things. So if you even need to be more precise, like more careful, then I think it will be much harder.
Can I ask a follow-up question?
Yes.
Somewhat related, maybe. So suppose I give you a quantum circuit and I ask what's the smallest one? Or is there a smaller one? How hard is this as a computation problem?
So it is definitely in QCMA, because like in this problem, we have a quantum proof, classical proof, and a quantum verification. Oh, good question. Let me think. Okay, let me think. I think, okay, okay, you're assuming also all your inputs are 0, right?
Yeah, let's say that's right. Yeah, let's say I just want to have two circuits that prepare the same state, for example, or I could ask other unitaries themselves, you know, other unitaries implemented by the circuits.
So
sorry, no, yeah, I have a say. You could ask the state question. Is there like a simpler way of preparing the same state, or you could ask the unitary question? I mean, whatever you like.
Okay, so then, okay, my conjecture that this is in QCMA because I can, so the input to this problem is a description of a circuit. And you know that this new circuit is just smaller than the description I give you, right? So then if I have these two candidate circuits, I think you can at least check if approximately they're creating the same state. Okay, do you want exact or approximate version?
No, let's say, I mean, either's fine. I think I just thought it's maybe interesting to give some intuition because, I mean, in some sense, this problem is something that you know, we make conjectures about. You know, so I think it's interesting to know how hard it is a computation problem itself.
So I'd guess that at least it's contained in QCMA.
Do you think it's hard for anything? Well, I guess it relates to all these questions about minimal circuit size and so on. So we don't maybe know.
Yes and no, right? Because okay, in this minimal circuit size, you're given a truth table, right?
Yeah, that's right. Yeah. So I mean,
you're given a circuit.
Yep.
It must depend on the class of the Hamiltonians that you are that build this unitary, right? There must be like some subclass for which it's easy, though. So yeah.
But I take it back about this connection with classical because also here you want to do it just for a fixed input, right? And not for any input. So it is a bit different from this classical problem.
Yes, I think you could study both problems. I think the Nielsen kind of thing is more like the whole unitary, but maybe, but other people spoke about, yeah, it's more about the state. Right.
Yeah, I think the hardness of this problem would be very sensitive to what's the setup. Like if it's the same input or if it's the different inputs for different circuits that generate the same output.
Thanks.
I have a basic question. Is the classical version of QMA, does it coincide with anything?
Sorry?
The classical version of QMA, maybe MA, does it coincide with AP?
So we believe it to be true, like the randomized one. Yeah, we believe it to be they to be equal, but we don't know how to prove it.
Okay, thanks.
And as I said, this is this is connected to this like complexity of these types of Hamiltonians. Like we believe these two to be the same, but we don't know.
I have a question.
Yeah.
So in many physics problems, we have a Hamiltonian for a lattice state. And we want to know if in the large volume limit, is there a gap between the ground state and the first excited state?
Oh, this problem, I think it was shown to be uncomputable. I think is Mari's in this result. I think Mari's in this result and he's in the audience. But yeah, this problem is very hard. You cannot even compute it.
So it's harder than QMA hard.
No, yeah, it's like there's no algorithm to compute it. Like even if it takes infinite amount of time, there is no time to compute it.
Even if there is no sign problem.
Oh, no. Okay, with sign problem. Let me think. probably with sign problem it is computable because then it's somewhat classical. No, okay, no. I conjecture. So I conjecture that for without sign problem, then you can solve it. There's an algorithm for it. I don't know the complexity of it, but it's definitely not. I conjecture that's not uncomputable. It's computable.
Any other question for Alex? If not, maybe we can stop this session, and thanks Alex again.
Thank you.